Good evening, everyone. Thank you for joining us this evening for Defeat Duchenne Canada's research grant announcement for 2026. We're grateful to have our community with us this evening, and also thank you for making your time to be here tonight. So, this evening is about progress, possibility, and people, about how together we continue to move Duchenne research forward. So, what you can expect from today's webinar is, first of all, we will begin with reflections from our founder, John Davidson, as we close our 30th anniversary year and honor the legacy that brought us here. We'll then hear from Dr. Hans Lochmuller, who will help ground us in the current research landscape for Duchenne. Next, we'll introduce our newly funded 2026 research grant recipients, who will describe their projects and why their work is meaningful for our families. And finally, we will come together to celebrate a major research funding milestone, one that would not be made possible without the incredible commitment from you, our community. I would like to sincerely thank our donors, fundraisers, corporate and industry partners, and volunteers. Defeat Duchenne Canada does not receive government funding, and everything you'll hear tonight is possible because of the people who believe in this work and in the families we serve. For those of you who may be new to Defeat Duchenne Canada, we are Canada's only national charity solely dedicated to ending Duchenne muscular dystrophy. Our vision, set 30 years ago, is simple and bold: a world without Duchenne. Our mission is grounded in our 4 core pillars, reflecting what families have told us they need most: research that drives progress in care and drug discovery that brings us closer to a cure, advocacy that ensures Canadians can access the right treatments and the right care at the right time, education to empower, community engagement and support to remind us all that no one faces Duchenne alone. So I'd like to tell you a little bit about our research granting cycle. So every spring, we launch the cycle with an international call for letters of intent. From there, proposals are reviewed by our Research Funding Advisory Committee and our Duchenne Family Advisory Committee. Shortlisted projects are then invited to submit full applications, and our final funding decisions are approved by our board of directors. It's a rigorous process by design because families and donors trust us to fund research with the greatest potential to have meaningful impact for our families. So a little bit about our committees. Our Research Funding Advisory Committee is made up of leading clinicians and researchers from across Canada and internationally. These volunteers bring deep scientific expertise and a shared commitment to the Duchenne community. So I'd like to call out and say a big thank you to Dr. Lisa Hoffman, who is from Lawson Health Research Institute in London and is our committee chair. Dr. Hernan Gonorowski from the Hospital for Sick Kids in Toronto. Dr. Eric Hoffman from the School of Pharmacy and Pharmaceutical Sciences at Bingham University, New York. Dr. Hans Lochmuller from the University of Ottawa and the Ottawa Hospital. Dr. David Mack from the Institute of Stem Cell and Regeneration Medicine, University of Washington, Seattle. Dr. Jean Ma from Alberta Children's Hospital in Calgary, and Dr. Toshi Yokota from the University of Alberta in Edmonton. We are deeply grateful for your time, care, and thought you bring to every decision. I just want to call out Dr. Hernan Gonorowski, who has stepped down from the committee this year, and I just want to thank him sincerely for his dedication and contributions. In his stead, I am very pleased to welcome Dr. Amanda Jaworski from the University of Ottawa Research Institute at the Children's Hospital of Eastern Ontario. Dr. Jaworski has already participated in our full application round this year, and we look forward to her continued participation in the coming years. Now, alongside our Research Funding Advisory Committee is our Duchenne Family Advisory Committee. And these individuals are the individuals who ensure that our proposals are also reviewed through the lens of our lived experience. balancing the demands of this volunteer program alongside parenting, school, work, all while managing life with Duchenne is no small feat. We are deeply grateful to all the families and individuals who give their time and energy to support this work. So I'd like to call out and thank Lori Power from Sydney, Nova Scotia, who is our uh, DFAC chair, Carrie Densky from Saskatoon, Saskatchewan, Nicole Matheson from Saskatoon, Saskatchewan, Kasha Mitten from Kamloops, BC, Darlene Morton from Oakville, Ontario, Eric Morton from Toronto, Ontario, and Rachel Witzke from Eggenville, Ontario. Thank you all. Next, I am pleased to introduce you all to Jennifer DeRamo. She is our newest member at Defeat Duchenne Canada and our new Director of Research and Education. Jennifer has spent years supporting families affected by rare diseases and translating research into real-world impact. Jennifer, we are excited to have you with us tonight. Jennifer will be leading our research initiatives moving forward. Jennifer, did you want to say a few things?
Sure. Hi, everyone. I'm Jennifer DeRamo. I'm currently living in London, Ontario right now, but I'm originally from Toronto. I joined Defeat Duchenne Canada only a few weeks ago as the new Director of Research and Education. My background is in genetic counseling. I'm a certified Canadian genetic counselor, and I've worked in the rare disease space for many years, both in the nonprofit sector and in the clinical space, including in the area of metabolics and newborn screening. My son passed away at the age of 10 from a very rare bleeding disorder, and since then I've been focused on rare disease research and education. In my new role at Defeat Duchenne Canada, I'm very excited to help strengthen both our pillars, the research pillar and our education pillar, support collaboration, and ensure that knowledge sharing remains central to the work that we do. And I'm honored to be part of this community.
Thank you, Jennifer, and welcome again to the team and to the Duchenne community. So I'd now like to turn it over to our founder, John Davidson, to say a few words. John?
Thank you very much. Every story, good or bad, has a beginning. And tonight, I want to take just a little bit of time to look back at how our organization got started and some of the milestones that have brought us to where we are today. I am not a researcher, but I'm going to do my best to add a few historical highlights that I hope will help shape the story. I'm sure as parents, we can all remember when Duchenne muscular dystrophy became a part of our lives. Although I didn't know it at the time, our family journey really began when our middle son, Jesse, was diagnosed with Duchenne in 1986. He was 5 years old at the time. But more than 150 years before that time, a Scottish surgeon, Sir Charles Bell, wrote an essay in 1830 about a disease that led to progressive muscle weakness in boys. For the next 40 years, that was all we knew. The disease didn't get a name until 1868 when French doctor Guillaume Duchenne became the first person to give a comprehensive account of 13 boys affected by a severe disease, which would later be referred to as Duchenne muscular dystrophy. When Jesse was diagnosed, I didn't know any of that, and I really didn't care. What I wanted to do was to help find a cure as fast as possible. And one of the first things I did was to ask myself, how does my buying a wheelchair help solve this problem? And the answer was, it doesn't. That's when I shifted my focus to research. I didn't know much about research other than the fact that I knew it cost a lot of money. I also knew that we needed to do something pretty big to capture people's attention and to kickstart our ability to raise money for research. After a lot of planning and with the support of family and friends who volunteered to help, in the summer of 1995, Jesse and I set out on the road, a father and son determined to make a difference. The goal was simple. The reality was not. Still, on those lonely days in Northern Ontario, where the hills were big and the donations were small, we really didn't know what lay ahead for us. We just kept pushing on day after day, hoping that somewhere there were people who cared about what we were doing. And there were. With every passing day, what had become known as Jesse's journey began gaining momentum, and we were receiving messages of encouragement from people all across Ontario and beyond. And it's worth noting here that during our journey across Ontario and in my walk across Canada, we did not have a website. The only way to make a donation was with the old familiar method of a check, an envelope, and a stamp, assuming you could find our address in London or come to the side of the road. And thousands of people did just that. With the Ontario Provincial Police and municipal police forces now escorting us, what began as a small groundswell was beginning to grow into organized chaos almost every day. I was pushing Jesse across Ontario in his wheelchair to raise money for research, and for the next 5 months in that time, that was exactly what we did in what was at that time the hottest summer on record. The first breakthrough on the research front that I was really aware of had come in 1986 when the faulty gene that causes Duchenne was identified. This was both good news and bad news. The good news was the discovery itself. The bad news was the size of the gene. It is huge. And at that time, it was the largest piece of genetic material to be discovered, 10 times larger than the next known gene, and 100 times larger than the average gene. Day after day, we kept telling our story, and day after day, people kept responding. And slowly but surely, our ability to fund research was starting to grow. And if there was one thing we learned that summer, it was this. When you are passionate about what you are doing, people will listen. And the more passionate you are, the more they will listen. We found out that we didn't have to be researchers to raise funds and awareness. We just had to care, and we cared. Everywhere we went, we took every opportunity that presented itself to put Duchenne muscular dystrophy firmly in the public eye and on people's radar when it comes to the things they want to donate to. By the end of summer, after 124 days together on the road, it seemed like everyone wanted to be a part of Jesse's journey and to reach out to the young boy who was showing people grit and determination of what real courage is all about. And I'll always remember Doug Gilmore leaning over and saying, "You guys are doing a really great thing." Even the Prime Minister of Canada wanted to share in the experience of making a difference. And it's people in the political world who have indicated to us their desire to help, and they will be hearing from us again. When we completed our journey across our home province, Jesse became a recipient of the Order of Ontario. You know, Jesse never played on a baseball team or a hockey team. He couldn't swim or use a skateboard, and Jesse never rode a bicycle. But what a difference he made for others. In 1995, Jesse's journey made people aware of Duchenne muscular dystrophy, and it raised a lot of money for research. But I knew it wasn't enough, and I knew I could do more. In April of 1998, I found myself in St. John's, Newfoundland, ready to try to walk across Canada. I wanted to build the Jesse Davidson Endowment to where we could make a major contribution to research every year. You learn very quickly that not only do we live in a beautiful country, we live in a very big country. I would find out just how big Canada is over the next 10 months on the road. Sometimes when we talk about Newfoundland, we often use the word island, and we mistakenly think to ourselves, it's just an island. It can't be that big. From St. John's on the extreme east coast of Newfoundland to Port aux Basques on the west coast, where you board the ferry to take you to the mainland, it is just under 1,000 kilometers. And in the snow and wind in April in Newfoundland, walking the Trans-Canada Highway isn't a lot of fun, especially when a lot of people had yet to hear about Jesse's journey and Duchenne muscular dystrophy. But I used every opportunity I had to share our story every day with service clubs, church congregations, school kids, business groups, and anyone who would listen. I saw this as a chance to plant the seeds that would grow research dollars, and that proved to be true. Day after day, I logged 33 kilometers on the road, making my way through Nova Scotia and across Prince Edward Island before crossing the Confederation Bridge and moving on to New Brunswick and then Quebec and with perseverance, people began to react. On my 112th day on the road, we reached Toronto. By this time, the road crew was operating like a well-oiled machine, and the number of research dollars was growing, and so was our ability to fund research as we are doing tonight. When I reached my hometown of London on day number 120, I saw my family for the first time in over 4 months. During the time of our road adventures, the Human Genome Project was picking up speed. This was a massive international effort to map and sequence all the genes in human DNA. As Duchenne parents, we have all probably been to the internet and seen pictures of the double helix of DNA that looks a bit like a twisted ladder. DNA had been discovered in 1953 by doctors James Watson and Francis Crick. This was really, in my mind, the first modern milestone in the history of science. The Human Genome Project had helped us to understand our complete genetic blueprint, identify genes, and to develop new tools for analysis, significantly impacting medicine and biology by revealing genetic variations. Knowing that some of the tools that research needed were in place drove me on to make these tools work for our boys as fast as possible. By the time I reached the Ontario-Manitoba border, summer was behind me. Ahead lay the prairies and 6 weeks of being able to look 360 degrees to the horizon. This is the part of Canada that was the most taxing mentally. But I knew I was here and I knew why I was there, and quitting was not an option. This is day number 225 on the Trans-Canada Highway. And on that day, the snow was blowing sideways across the Trans-Canada, and it was the only day on that entire journey across Canada that not one car stopped to make a donation. Still, I pushed on and on until I reached the Pacific Ocean in Victoria, British Columbia. After 286 days on the road, I reached Beacon Hill Park in Victoria. Jesse's journey has established itself as Canada's leader in funding research. Jesse's journey has gone on to become Defeat Duchenne Canada and now is a family of families from coast to coast. Research is moving forward from prednisone and deflazacort and now focuses on things like gene therapy, exon skipping, and CRISPR, the restored dystrophin, with several treatments gaining FDA approval in recent years. In Canada, Health Canada has recently approved Amagre, first known as vamorolone, a drug that Defeat Duchenne Canada invested in almost 5 years ago. We were able to do this because people like you and your family and your friends have helped generate the research funding that is driving us forward. I hope this has helped tell the story about how we reached where we are today. And while Jesse did not live to see the advances that are happening now, you are his legacy. And from everyone at what I suppose I can probably be forgiven for still calling Jesse's journey, now Defeat Duchenne Canada, where we are making great strides forward. And as Jesse's dad, I thank you all for making that happen. Thank you very much.
Thank you, John. Your story and Jesse's story is an inspiration to us all and the very reason we are all here today. And it'll always be Jesse's journey as well as Defeat Duchenne Canada.
Thank you.
I would like to now introduce Dr. Hans Lochmuller. Dr. Lochmuller is a neuromuscular specialist at the Children's Hospital of Eastern Ontario, professor of neurology at the University of Ottawa, lead investigator of the Neuromuscular Disease Network of Canada, a board member of Defeat Duchenne Canada, and in his spare time, a valued member of our Research Funding Advisory Committee. We've asked Dr. Lochmuller to provide an overview of the Duchenne research landscape. Thank you, Dr. Lochmuller, for your time today. Oh, we're just getting your slides up.
Yeah, thank you so much for the kind introduction, Nicola. And I'm wondering whether you can see my slides already.
Can you go into presentation? There we go. Perfect.
All right. So yeah, an amazing story, and I love to hear it again and again from John. Thank you so much, and I'm proud to be a part of this organization. So what I want to do in the next few minutes is to give you a little overview of the Duchenne research landscape to help you uh, understand some of the terms because some of it is quite technical, but it hopefully will set the scene for what we're all waiting for with excitement, which is the new projects that will be presented later on, so you can put them in context. So we already heard from John that the dystrophin gene is one of the largest genes still in the human body. And the gene is encoded in the DNA in that double helix that gets transcribed into what's called a messenger RNA. And that will be important later on for some of the therapies. And then the RNA is being translated into what we call the protein or the dystrophin protein, which is still a fairly large protein. It's maybe not the largest protein in the body, but a fairly large protein that uh, sits underneath the cell membrane of all the muscle fibers. So in the lower right, you see a cross section of a tiny piece of muscle under the microscope. And what's red in these polygonal muscle fibers, that's a stain for dystrophin. So if we look at the muscle of a patient with Duchenne muscular dystrophy, then this protein is missing. And the reason for that is because there's a fault mutation in the dystrophin gene. Therefore, no RNA or the wrong type of RNA is being made, and no protein originates from that. And this is shown in the lower right. So basically, none of the muscle fibers shows a stain for dystrophin. While on the upper right, again, this is an image from a person that does not have Duchenne. And if you look on the left, you have a same kind of image of a cross-section of a muscle biopsy, but it shows how the muscle fibers look structurally. So in a normal muscle, all the muscle fibers have a similar shape and form. There's very little other tissue in between, while in the muscle biopsy from a patient with Duchenne, you see, and that's in the lower left, you see a lot more irregular images with small fibers and large fibers, then fibers that stained darkly red, which means they have too much calcium. And then there's more space in between the fiber. This is a scar tissue, fibrotic tissue. And then there's areas where there's a lot of tiny little cells, blue dots on the left-hand side, which means there's a lot of inflammation in this Duchenne muscle as well. So a lot of these things were discovered before the gene was even known, but now we have a much better understanding how the defective gene and the loss of dystrophin leads to all these abnormalities, to the wasting of muscle, and then to weakness consecutively. So the way we develop therapies nowadays is that we test them rigorously, first in tissue culture often, then in animal models, and then it goes into clinical trials. And they start with small numbers of patients where just the principle of the therapy is being tested and how much of the therapy is safe to give. And then going to larger trials where we want to understand whether the therapy is effective and there's a long-term benefit to be expected for the patient. So this also means that through this rigorous step-by-step approach, it often takes a long time for therapies to reach patients. So even so, the gene, as John explained, was discovered 30 years ago now. There is still a lot of things that we discover and find out, and where we find also new ways and approaches to develop therapies. So, and I'll explain some of the approaches, not trying to give you every single therapy here. So it's just sort of in rough strokes that you see where to place some of the things that we are talking about. So this is a similar picture where you have the cell with the DNA, the double helix, and that's making the RNA, which is sort of the molecule in the middle, and then the green blob down there, that's the protein. And as you heard, the gene has the mutation. So the logical thing is, well, then let's fix the gene, correct the gene itself, and that's what's called genome editing in CRISPR. And that's a technology that only more recently became available. And this technology works currently and is approved for some genetic conditions whereby you can actually remove the cells from the body of the patient first, then apply your CRISPR, and then put the cells back into the body. But in terms of Duchenne, that's not an option that we really have. So therefore, this is something that's in the, I would say, more early stages of development, but it's definitely a very interesting therapy, and it's in parts pioneered in labs in Canada and funded by Defeat Duchenne. The next approach that's out there for a little longer is, well, if you cannot correct the gene itself, why not put in a new gene, a functioning gene? And that's what we call gene replacement therapy. And the most common way to do that currently is by using a modified virus that transports genetic material into the cells. The most common vehicle for that is called adeno-associated virus, but there's work ongoing to maybe use other types of vectors, and you'll hear about this later. So how does that work? So the AAV infects the muscle fibers and transports the gene into the muscle, and then that makes new RNA and functioning protein. So there is, in fact, one of these gene therapies with AAV is approved in the US, but not in Europe or in Canada. It is a single intravenous infusion with a very large number, a high titer of AAV harboring a microdystrophin gene. So this is not the full dystrophin gene because it doesn't fit into the AAV, but a small version of it. There is a degree of protein made from this, but it's variable. And there's potential toxicity to the liver because of this high titer AAV. And there seemed to be an even higher risk in older children, and there have been some fatalities in clinical trials. So there is a risk associated with it. The functional long-term benefit from this current therapy is more difficult to confirm, and some phase 3 trials have actually not shown the same benefit. So there's currently new types of AAVs with lower toxicity and enhanced immunosuppression to reduce the risk, trials ongoing. And as you will hear later, there's maybe also ways not to use viruses, but other tools to get functioning genes into the muscle fibers. Another therapy does actually not aim to fix the gene itself or put in a gene replacement, but in fact correct the RNA, because if the RNA is corrected, then you can still make a functioning protein, and that's what we call exon skipping. And this again works through in infusion, in intravenous infusion with so-called antisense oligonucleotides. And they have been around for a while now, and several of them have been approved in the US and in Japan, but none in Europe or in Canada. What needs to be known about these AONs is that they are mutation specific, so not everybody with Duchenne benefits from exactly the same AON. So there's groups of patients that benefit from a specific antisense oligonucleotide. That's why it's a large group, and it's important to know exactly what mutation would respond to which kind of antisense oligonucleotide. The current ones require weekly intravenous infusion. The dystrophin restoration is relatively low, and again, the functional long-term benefit is difficult to confirm. Again, the research has moved on, and there's now a new class of coupled antisense oligonucleotides that uses a trick by linking the antisense oligonucleotide to an antibody or to certain peptides that help them to have a better uptake into the muscle fibers. And in animal models and in early human trials, that shows a much better dystrophin restoration. And there's trials ongoing, including several trials at Canadian sites. Coming to the type of drugs that's around for the longest time and which is standard of care in Canada and elsewhere in the world, and these are the so-called corticosteroids. This is the prednisone and the deflazacort that John has mentioned. So they do not restore dystrophin, but they dampen the inflammation that's in the muscle that I showed you. And they have shown to help muscle to uh, slow down degeneration and to stay intact for longer. However, they do come with certain side effects if they are taken long term. Um, and these side effects are seen in a lot of the boys with Duchenne. Not in everyone to the same degree, but there's weight gain, bone fragility, growth stunting, suppressed immunity, and mood changes. So there's a real trade-off to these therapies. So therefore, Dr. Eric Hoffman and colleagues have developed a new type of steroid, which does retain the benefits of the classical steroids, but has fewer of the side effects, particularly in relation to the bone and to the growth. And this is vamorolone that was mentioned. And this is, in fact, now the first drug that's approved for therapy in Canada and will become commercially available later this year. And this is a major milestone, and Defeat Duchenne has played a big role in this research and bringing this research to Canada. So I stop with this. It's just setting the scene, and I hope you enjoy the rest of the evening.
Thank you so much, Dr. Lockmuller, and that was excellent. Thanks for summarizing the treatment landscape. I know that's not an easy thing to do in a short period of time, but it's really great to see the progress that's happening in research, the treatments that we see for Duchenne, and also the hope that lies ahead for our families. So it now gives me pleasure to introduce Dr. Lisa Hoffman. Lisa is the chair of our Research Funding Advisory Committee, and she is going to introduce our current as well as our new research recipients. Thank you, Lisa. Are you on?
Yes, I'm on.
There you are.
Okay. Thank you, Nicola. I've been a volunteer with Defeat Duchenne Canada, then Jesse's Journey, for about 13, 14 years. And I must say, this is my favorite time of the year. Before I introduce this year's newly funded projects, I'd like to take a moment to acknowledge the incredible work already underway. So we have 8 researchers who completed their funding in 2025, including Dr. Leanne Ward from Ottawa, who is leading a 3-year clinical fellowship focused on improving bone health and hormone care for people living with Duchenne. Dr. Francesco Montoni from the UK is studying what happens in the body when dystrophin, the protein missing in Duchenne, is not present. Dr. Natasha Chang from Montreal is studying how protecting muscle stem cells from stress can help muscles repair themselves more effectively in Duchenne. Dr. Ronald Cohen from Toronto is testing a 2-part approach that utilizes gene editing to correct the Duchenne causing DNA duplication alongside steroid treatment in a mouse model. Dr. Rashma Amin, also from Toronto, is creating a national system to better collect and connect patient-reported data across Canada. Dr. Jacques Tremblay from Quebec is developing a highly precise gene editing technique to directly fix the genetic mutations that cause Duchenne. Doctors Aoki and Sather Prakash from Japan are using patient stem cells to grow mini brain models in the lab to better understand how Duchenne affects learning and cognition. And Dr. Alain Stincy from Ottawa is in his final year of funding. He is investigating the function of gut microbiota in Duchenne mice and assessing whether increasing the levels of beneficial bacteria can improve muscle strength. Each researcher building momentum and deepening our understanding of Duchenne. We've invited these researchers to share brief video updates of their progress. These updates will be emailed to you after tonight's event, and we encourage you to take a few moments to watch them. So this year we received 20 letters of intent from Canada, the USA, the UK, Israel, and Europe, reflecting both the global urgency of Duchenne research and the strong reputation of this program. 10 applicants were then invited to provide a full application, of which 8 were completed for consideration. Following the review process, including scientific assessment and family perspective, the RFAC and DFAC recommended 3 exceptional projects for funding. Our first new grant recipient is Dr. Jim Dowling from the University of Pennsylvania. Dr. Dowling will receive $400,000 over the next 2 years for his project entitled Non-Viral Gene Therapy for Duchenne Muscular Dystrophy. This project explores innovative approaches aimed at addressing the genetic root of Duchenne. And before I turn it over, I'd like to encourage everyone to post their questions into the chat, as we'll open it up for questions after each speaker. Now, without further ado, Dr. Dowling, I'll turn it over to you.
Thanks, Lisa. I'm going to share my screen. Can everyone hear me okay?
Yep, we can hear you well.
Great. All right. So first, I want to say it's a great privilege and honor to be presenting today and also to receive a funding award from Defeat Duchenne. I have the privilege of having been involved with Defeat Duchenne for many years previously as a member of the Research Advisory Committee, and got to work with Lisa and several others on that. And also actually my interaction with Jesse's journey goes back to my time in Michigan when I first heard about it before I was a clinician at Sick Kids now 13, 14 years ago. So it seems a bit full circle to be coming now with a research project, and really excited about the project, and also very honored to have received a funded grant. So I want to just give a bit of the highlights of what the challenge that we're trying to address and what we're hoping to accomplish over this next 2 years. And I should mention this is a collaborative project between myself and Dr. Drew Weissman, who's a prominent clinician scientist researcher at the University of Pennsylvania. So Hans, Dr. Lockermiller really introduced this topic, so I don't really have to go over this, but he highlighted the many different potential opportunities related to what I would consider the overall class of genetic medicines to treat Duchenne muscular dystrophy, and highlighted as well the challenges that these types of therapies are facing. So I think about these in as being kind of two compartment therapies. There's the cargo, and that's the actual therapy that's being delivered, whether it's a small RNA like an antisense oligonucleotide, whether it's a gene itself and gene therapy, whether it's a gene editing reagent like Cas9 or one of the CRISPR reagents. And then there's the vehicle to deliver it. And in skeletal muscle diseases and Duchenne in particular, the big challenge has been that delivery vehicle. It turns out that it's very difficult to deliver medicines to all the skeletal muscles in the body. The current delivery strategies all have various shortcomings that really open up the question and challenge of whether new and different and effective delivery vehicles could be developed. And that's the goal that we're trying to address. So there is a delivery vehicle out there that is quite ideal in many ways, and that's called a lipid nanoparticle. And these are pretty ideal in terms of delivering the full range of genetic medicines. And so these are encapsulated lipids that have several different potential components in them. And they are a delivery vehicle that can very well encapsulate nucleic acids of many different sizes, everything down to the small antisense oligonucleotide that Dr. Lockme was talking about, to theoretically the entire dystrophin gene. The great things about them is that they are safe with very low toxicity. There's a lot of experience in humans of receiving lipid nanoparticles very safely. They're relatively inexpensive to manufacturing, which has been a challenge with some of the other genetic medicine strategies in AAV gene therapy in particular. And they're also very tunable. You can give them repeatedly. You can deliver some therapies that only need to be given once, but you can also have things that you can give multiple times and do that safely and effectively. So these are, again, all the different types of things that could be delivered with a lipid nanoparticle. So everything from those antisense oligonucleotides, which can be more effectively encapsulated and delivered in ASOs and given by themselves, all of the gene editing reagents, and then gene replacement therapy with full-length mRNA. So the big challenge with lipid nanoparticles is that they love to go to the liver when you're given IV, and unfortunately don't like to go to many other tissues, and in particular, don't go very well to the heart and the skeletal muscle, which is obviously the critical tissues for treatment for Duchenne. This has been the big barrier in the field of non-viral delivery for skeletal muscle disorders. In that whenever one gives these lipid nanoparticles to whether it's an animal model or to a human, they essentially go primarily to the liver. So this is the challenge that we're trying to overcome with our grant proposal. And our goal is to create really the first effective and safe muscle targeting lipid nanoparticles and to use those nanoparticles for the delivery of key genetic medicines for the treatment of Duchenne muscular dystrophy. And in particular, we are seeking to use this as a strategy for an alternative to gene therapy and to use it as a way to deliver the full-length dystrophin mRNA as a gene replacement strategy. So this is how we're going to do it. This is a very busy slide, and I apologize for that. But we're doing this in two different aims. The first aim is to develop our muscle targeting lipid nanoparticles, and we're doing that through a very comprehensive and systematic process. Where first we're creating a library of different lipid nanoparticles, and the library will differ based on the composition of the lipids, but most importantly, by the presence of targeting antibodies. And we've selected a library of antibodies that we will recognize things that are on the skeletal muscle already, and basically serve as honing devices for the lipid nanoparticle. So basically adding a signal onto the nanoparticle that will then match a signal that's present on muscle as a way of drawing the nanoparticles to the muscle. We're also trying to innovative strategies to detarget the liver. One is to remove the parts of the nanoparticles or the receptors on the liver that contribute to nanoparticle uptake in the liver. And the other is to try to enhance the delivery of nanoparticles to muscle by creating increased blood flow into the muscle beds. Once we've developed these library of nanoparticles, we're going to test them systematically in a mouse model. And this is work that has to be done in an animal model because doing them just solely in cells does not recapitulate the challenges of the barriers to the delivery. So it's very easy to actually get nanoparticles into muscle in a dish because you've removed the things that prevent nanoparticles from going to muscle in a whole body. And so we're doing all of our screening in the mouse as a model system, and we're first just screening for the best nanoparticles to go to muscle, and then we'll do a secondary screen using a clever marker mouse that enables us not only to tell whether or not we're delivering, but also enables us to see whether we're delivering to the stem cells and the satellite cells, and also to which percentage of the muscle nuclei that we're delivering to. And in this way, we're able to develop the best muscle targeting lipid nanoparticle. And once we have that, we will then go on to test for safety and effectiveness, mRNA-based gene replacement strategy for Duchenne, encapsulating the full-length dystrophin mRNA into our best lipid nanoparticle, and then delivering it to the MDX2V mouse model of Duchenne muscular dystrophy. And this is basically the paradigm in which we will do that. So as I mentioned, this is something that has not yet to be really successfully done. And so why do we think we can do this when others have maybe not succeeded in that space? And that primarily has to do with the very strong track record that we have, and in particular that Drew Weissman's group has in developing targeted nanoparticles. So he is now successfully, his group has developed lipid nanoparticles that target several different hard to target tissues, including the endothelium, the immune T cells, and also to several stem cell compartments. And so the main strategy that he's employed and that we will employ in this proposal is to add these tags onto the lipid nanoparticles. In this case, showing an antibody tag that enables that honing of the nanoparticle to the tissues of interest. And interestingly, adding these tags also by themselves somehow detargets the liver. So whenever you put a tag on a nanoparticle, it tends to make less of it go to the liver. So you accomplish two things: directed targeting to your tissue of interest and detargeting of the liver. And so a recent example of how the Weissman group has done this is by adding antibody tagged lipid nanoparticles that hone in on these immune cells called T cells. And he's used these to deliver specific receptors to turn T cells into CAR T cells as a potential anti-cancer therapy. Right now, CAR T cells are used on an individual basis, but they require the removal of the blood cells from the body, then the targeting, and then the adding back. And this strategy to be done in an individual without actually having their T cells removed. Actually, there is some applications of the specific strategy related to fibroblasts and fibrosis that is a secondary consideration with nanoparticles for treatment of Duchenne, but is outside of the scope of the current proposal. This is just showing the effectiveness of these in vivo CAR T cells that are done through the targeted lipid nanoparticles and how they can be used to deplete a specific cell population in the spleen. Probably more relevant to our proposal at hand is the fact that the Weissman group has developed heart targeting lipid nanoparticles. And this gives us a lot of encouragement that we can similarly develop skeletal muscle targeting lipid nanoparticles. And at the very least, we can build off of these nanoparticles as a way to start treating the cardiomyopathy of DMD. And so in this study showed both the effectiveness of adding a specific type of lipid, a different kind of lipid within the nanoparticle to make ones that go to the heart over a standard formulation, and then also using this lipid detargeting strategy of reducing the amount of ApoE to detarget the liver. And that's just an example of how it was used to effectively deliver an siRNA, so a small RNA therapeutic, to the heart to produce gene knockdown. So you could imagine a similar approach could be used to deliver an antisense oligonucleotide to promote exon skipping for DMD, or again, to deliver the full-length dystrophin mRNA. So to summarize, we have previously demonstrated the ability to target nanoparticles in hard-to-reach non-liver organs and tissues. We have been able to deliver a range of genetic medicines using these nanoparticles, including ASOs, CRISPR reagents, and mRNA. And we've shown that the combination of antibody targeting with this ApoE knockdown both detargets the liver, but also enhances targeting to tissues of interest. So we propose to use the same strategy to achieve muscle targeting. And just to give a little teaser, and this has been in collaboration with and through a previous grant that we had with the National Research Council in Canada, we have developed some nanoparticles that are showing some muscle targeting. They're not optimized, and we have a lot of work to go. But we have been able to show the ability to deliver not DMD, but a smaller transgene, the MTM1 gene, which is a disease-relevant gene, using nanoparticles after IV injection to go to the muscle. And that we've been able to show that these can ameliorate parts of the phenotype of the mouse model of X-linked myotubular myopathy, which is caused by loss of the MTM1 gene. So we can add back MTM1, and that can produce some benefit. So this gives us the first hint that our strategy of tagging lipid nanoparticles can overcome the barrier of muscle delivery and develop muscle trophic nanoparticles. So to summarize, there's in my opinion, a critical unmet need to develop new delivery vehicles for the treatment of Duchenne. Lipid nanoparticles offer great promise, but historically have not been able to be targeted to skeletal muscle. Based on previous success in our preliminary data, we believe that we will be able to develop very potent and safe muscle targeting lipid nanoparticles that will then open up the entire universe of genetic medicines for the treatment of Duchenne. And with that, Defeat Duchenne for supporting this project, and we really look forward to embarking on this endeavor and within our 2-year period delivering lipid nanoparticles that can treat DMD.
Thank you, Dr. Dowling. That was great. So it looks like we don't have any questions at the moment, but we encourage everyone online to continue to add your questions throughout tonight's presentation. The second new grant recipient is Dr. Laura McAdam from Holland Bloorville Kids Rehabilitation Hospital in Toronto. Dr. McAdam will receive $25,000 this year for her project entitled Youth Helping Youth, Dissemination of a User-Informed Bullying Resource for Youth with Duchenne Muscular Dystrophy, focusing on psychosocial well-being and peer support, areas that families consistently tell us matter deeply. Dr. McAdam, over to you.
I'm just going to share my screen. Should be coming up shortly.
Yep, we see it.
Okay, so you're seeing my slides. Perfect.
Yep.
Excellent. So thank you for the introduction. Similar to Jim Dowling and Hans Lockmuller, I've had a long relationship with Defeat Duchenne Canada, and we were able to participate in the Family Forum this past fall, which was an incredible opportunity to meet individuals across the country, as well as continue or having ongoing collaboration with Defeat Duchenne Canada. So today I'm going to be talking about youth helping youth, a dissemination of a user-informed bullying resource for youth with Duchenne muscular dystrophy across Canada. So this project is focused on several pillars of the strategic plan for Defeat Duchenne Canada. The original project was grounded in community engagement, and it really started as a discussion in clinic with youth and their families, which grew into a research project, which I'll be highlighting, and which created the foundation for our knowledge translation project, which is the grant that was submitted to Defeat Duchenne Canada. So when we're thinking about bullying, what is bullying? It is an unwanted aggressive behavior that involves an actual or a perceived power imbalance. It's repeated or likely to be repeated and may cause harm or distress to the victim. We know youth with disabilities are 1.5 times more likely to be bullied compared to youth without a disability. And for the initial project, we didn't know what that meant from a rate perspective. There are many different types of bullying, and it can include physical, verbal, social, or cyberbullying. So in the initial study, this was done in collaboration with Hans Lockmuller and Hugh McMillan with CHIO, and we surveyed individuals with multiple types of neuromuscular conditions, but the majority had Duchenne muscular dystrophy. We then offered for these individuals to participate in an interview to let us know about their experiences, and this led to the creation of a resource, which is the foundation for this project. So one of the questions we asked was, in my life, was how have they been bullied? So what the youth told us is, in my life, I've been bullied a lot. So 83% of the respondents experienced bullying at some point in time in their life. When we asked about the individual types of bullying, none of them expressed cyberbullying, but 30% described physical bullying, 88% described verbal bullying, and 83% described social bullying. So this is a very significant issue that the youth with Duchenne are facing. When they were telling us about their experiences, they talked about, in my life, they've been bullied for many different reasons. And so disability was one of their most common reasons. So 63% identified that their disability was the root issue from bullying, and 54% discussed appearance. And when we were asking questions in the interview, they were talking about weight. They were talking about the distribution of weight as common changes in their appearance that was a target of being bullied. Additionally, their height. So 86% told us that bullying was a big deal for them and we needed to be doing something clinically. 90% identified it's the bully's fault. So when we're thinking about our target audience, that's important. 73%, when they were telling us what may be helpful, they talked about anonymous phone lines to report bullying. And 69% felt that having parents, students, and staff talking about these solutions would be helpful. In the interviews, several themes came up. And so the first one was talking about individuals experiencing stigma-based bullying. So one of the quotes from the participant said is, "If I can walk, why am I in a wheelchair?" So they were just laughing at that at the time, as if I'm all the time if I'm in a new class. So they're really highlighting a new peer group and not really understanding why sometimes they're in a wheelchair and why they aren't in a wheelchair. Now, stigma-based bullying is really the intersection between bullying, which is that intentional, targeted, repetitive behavior, and discrimination. And so in this circumstance, it's discrimination because of the physical condition that they have. They also talk about, a key theme was the resilience that the individuals had when they were telling us about their experiences. So one said, "I basically just talked about it with my parents, and I tried to find a solution on my own because I don't like asking people to help me to do things." So talking about the independence piece, coming up with solutions. So if I find a solution by myself, good for me. So really taking pride in that. And this is just one of the many quotes talking about resilience. They also identified personal and theoretical, helpful and unhelpful supports. So what was helpful was I talked to my mom and my friends, and they're really supportive, which helped me with the bullying. And unhelpful supports. You know, it's very often nobody's around us during school, so it's nobody that can notice the bullying that they're experiencing. So really highlighting that there isn't going to be a single prong when we're looking at addressing bullying for these individuals with neuromuscular conditions. They also talked about bullying interventions. So, both through the qualitative and the quantitative part of this study, we've come up with a bullying resource that's informed by the voices of youth with Duchenne and other neuromuscular conditions, as well as their parents. And these grouped into several different recommendations. So, focusing on youth, focusing on families, focusing on clinicians, and focusing on schools. And when this resource was developed, we had input from both youth, the parents, and healthcare providers and teachers to ensure that what we saw in the study also resonated with the individuals when the information was being reflected back to them. So this project is looking at the implementation of this resource. So this is knowledge translation, so very different than the basic science that we've heard about. And it's really about helping individuals where they're at, ensuring they have the information that will be helpful for them. So this is a 4-step project over the next year. We're going to prepare the resource for dissemination. So we need to make sure it's accessible in a language standpoint, in a format standpoint. It's going to be translated into French, and it's going to be compliant with the Accessibility for Ontarians Disability Act. Once that has been completed, we're going to use a knowledge translation or knowledge implementation framework called PRISM. And using this framework, we're going to be developing a dissemination plan and implementation plan, and then disseminating this resource. And at the end of this implementation science framework, they use the RE-AIM framework, and this is evaluating the resource reach and impact from a scientific standpoint. So for this project to move forward, we had engagement of youth and families with neuromuscular conditions to understand the scope of the issue and to develop a resource. And now I'm looking for engagement across Canada for both, once again, for individuals that have Duchenne muscular dystrophy, their families, advocacy organizations, as well as neuromuscular clinics to provide feedback on this resource, establish facilitators and barriers to implementation, draft and improve the implementation plan, and provide feedback of this implementation plan. So if there's anyone on this call that is interested, please feel free to reach out to me. My email is at the bottom here. My email is also on the website for Hall and Blur Review. I would love to hear from you. It can be anything from an email communication or participating in focus groups to help move this forward to ensure that this information is widely available across Canada as well as for people internationally. So I would like to finish up by thanking Defeat Duchenne for considering this project, recognizing that it's not a basic science project, but it's a knowledge translation project. And really, we've heard from youth and families with Duchenne about this issue and that it's a significant issue. We've created resources with their ideas, and now we want to ensure that individuals across Canada have access to the information. So thank you so much.
Thank you, Dr. McAdam. There is a question for you. I really like the holistic approach to the resources. Will the resources share scenarios and tactics to approach? Will there be any video assets?
So for this project, we haven't we haven't asked for specific funding for video, but I think that is an excellent idea for the next phase. There are scenarios based within this resource, and they have many practical ideas. I think no resource when we're focusing in on bullying is going to have all the different ideas, but I think if it could be idea generating and in collaboration with family members and schools to come up with what the right solution is for the individual that's experiencing bullying. But if you would like to be part of this or hear more about it, please reach out to me and I can absolutely find time or share further information.
Great. One more. Can you tell us more about PRISM? How will you collect data on the resource's usefulness to each target audience?
Yeah, absolutely. So PRISM is really a framework when we're looking at barriers and facilitators for implementing this across Canada. And that's why I need a broad focus group to be able to identify, because I think there are going to be different challenges in different places or different areas of the country. Now, when we're looking at evaluation using the RE-AIM framework, on all of these resources, we are going to have a specific QR code that people
No, I
can
didn't.
scan and give us
Well, I don't
direct
think I did.
feedback.
I have the agenda.
And we're also able to look at number of downloads from our website, as well as
Yeah, I'm hoping they're
if
gonna
there are
cut
clinics that
in.
agree to share this resource, they can let. I don't know, I was muted. Hopefully, people heard me when I was speaking.
I think we lost you there for a bit.
Um, there are several using the REAIM network, or sorry, the REAIM framework, as well as collaboration with clinics disseminating the information. We'll be able to understand the number of downloads from websites, the number of resources that have been provided, but we also want to hear information for people who have been using these resources. So there'll be a QR code where people will be able to provide their feedback. And I think when we're thinking about KT, there are always these cycles. So if we're hearing important feedback, we'll be able to adapt it within the resource.
Fabulous. Great. Um, well, there is a question for Dr. Dowling. Maybe we'll just come back to him right after Dr. Spurney's talk, and then we'll open up the floor to questions for all three of you again, if that's okay.
Lisa,
All
we
right
have
then.
one more question for Dr. McAdam, actually.
Oh, we do.
Yeah. Uh,
Um,
the question is, are you looking to create a resource that is standardized throughout Canada?
Yeah, so this is a resource that will be available for all across Canada. The resource is informed from the initial research study, so we have a good framework, but I'm really looking for engagement across Canada to review the resource. If there are any ideas to make it more relevant for different regions of Canada, I would love to have that feedback.
Fabulous. Great. Thank you so much. I guess Dr. Dowling needs to leave soon, so let me ask the question to him now. So can your potential treatment work with exon duplication?
So the short answer is yes. So if we successfully develop muscle targeting lipid nanoparticles, there's a very broad range of types of therapies that could be encompassed within them. So some of the strategies for treating duplications, including using CRISPR-Cas9 editing to cut out the duplications. There's also some use of alternative start sites with CRISPR activation. Any of those reagents, the gene editing reagents, fit very well in the nanoparticles, and it overcomes the problem that the viral vectors have, which is that the editors are often too big for the AAV gene therapy. So, in principle, yes. And while we're focusing on the mRNA therapy approach, because it would be mutation agnostic in terms of treating DMD, we plan to make the nanoparticles available broadly so that individuals working on other strategies can take advantage of this as well. So yeah, I guess a long way to say shortly, yes, the duplication strategies could be treated with LNPs.
Fabulous. Thank you so much. Okay, so our final recipient this evening is Dr. Christopher Spurney from Children's National Medical Center in Washington, D.C. He will receive $200,000 over the next 2 years for his project entitled Does Vamorolone Delay Cardiac Disease and Rescue Puberty in DMD? Exploring critical questions related to long-term health outcomes and quality of life. Dr. Spurney, please go ahead.
Okay, great. Well, thank you so much. Let me pull up my presentation here. All right, good. Everybody can see that okay?
Yes.
Perfect. I am a pediatric cardiologist. I am a newcomer to Defeat Duchenne Canada. I am extremely grateful to hear that amazing story about its founding and kind of the journey that it's gone through and how its research support has increased. And I'm certainly honored to be the recipient of that research and thank the committee for their work reviewing all the applications. This certainly may have some additional interest to Defeat Duchenne Canada because the work does study vamorolone. And as Dr. Luckmuller spoke about earlier, this is a steroid type drug that has recently been approved and was invested in by Defeat Duchenne Canada. So just to start off, again, steroids, they are our current standard of care. They are kind of a shotgun approach, but they decrease the inflammatory responses in skeletal muscles. This limits the disease extent and prolongs ambulation times. Certainly from my standpoint, right, we think about the heart, and there have been many studies that have demonstrated that steroid treatment is beneficial for the heart, and it can delay the onset of heart disease. And so certainly we are happy to see patients treated with steroids from a heart standpoint. What was mentioned also was that steroids do have significant side effects, and these can have a big impact on quality of life. Listing out here, you saw these a little earlier: obesity, these Cushingoid features, hirsutism, insulin resistance, osteoporosis, mood disturbances, stunted growth, delayed puberty. So many side effects that can often lead to people either stopping steroids or wanting to change. And that's, a lot of research has been about different steroid protocols. So vamorolone kind of came out of this concern for steroid side effects and effects on quality of life. And it's a novel steroidal compound that's anti-inflammatory. And it has the data to get approval by the FDA for 2 years and older for use in DMD. And then internationally, it's approved, and I guess Canada coming up, 4 years and older. As was mentioned, vamorolone has shown similar benefits to skeletal muscle function and outcomes similar to prednisone, and then showed an improved safety profile, less side effects. And there was a lot of focus on less stunting of growth and less mood disturbances. There's the website there if anyone wants to kind of go and learn a bit more about it. I pulled the kind of images of the structure just to go through a few details that are pertinent to us. You can see at the top here, the green circles. This is vamorolone, and it has these 2 green vertical lines. This is a indication of a double bond between these carbon atoms. And if you look down here at prednisolone, deflazacort, or classic steroids, you can see there's a single vertical line and then this other little OH group that hangs off the top there. And so it's really just this little difference that we have found to be the benefit in the side effect profile, is just this change in structure. So it has this unique structure difference, and that has changed some of its activity. Because it lacks that OH molecule that's hanging off the top. It's not really modified by some of the normal steroid enzymes that are in the body. It also does not bind the glucocorticoid receptor. That's the receptor where steroids bind. So it binds that less effectively, and that is likely related to its less steroid profile or less side effect profile. And then this last one is what has become of interest to a cardiologist, is that it's found to have a mineralocorticoid receptor antagonism. That's kind of a mouthful. If we were all in the same room, I would make everyone say it together. I will stumble over it at some point during the talk. But the mineralocorticoid receptor is a specific one in the body that reacts to different hormones. Looking at the images to the right, you can see progesterone at the top here is a strong antagonist. So the same thing, an antagonist is something that blocks or decreases the activity. And comparing that to the compound to the right that is an MR agonist, or it stimulates that receptor. And you can see the difference again is that there's no OH group hanging off the carbon bond there. And so vamorolone has this exact same structure without the OH hanging off. And so that's why it was kind of predicted to be an MR receptor antagonist. So we did some work quite some time ago at Children's looking at this potential activity. We used the MDX mouse model, which was also mentioned earlier. This is a dystrophin deficient mouse model. And we took that mouse and we challenged it with aldosterone. Aldosterone is a hormone in the body that increases blood pressure, increases fibrosis in the heart, increases salt levels. And so it has negative effects on the heart. And so we took the MDX mice and we treated them with aldosterone. And then we also treated them with other medications. One was vamorolone, and then the other two were spironolactone, otherwise known as aldactone, and eplerenone, known as Inspra. These are two well-known mineralocorticoid receptor antagonists. Some of you may be on them yourself if you have issues with your heart. Some of you with children with DMD, they may be on one of these drugs already as part of their cardiac therapy. And so we compared vamorolone to see if it had activity similar to those two. Panel A is looking at heart function. WT means wild type, so those are just kind of normal mice. And then the MDX is this dystrophin deficient mouse. So we treated the MDX mice with aldosterone, and this red box is how that mouse reacts just to the aldosterone. The heart does not like it, the function decreases. The blue boxes are the mice that are treated with these other drugs, vamorolone V, eplerenone E, and spironolactone S. And you can see that all three of those drugs kind of block these negative effects of aldosterone. The middle panel is demonstrating cardiac fibrosis. The fibrosis is the red staining. The kind of orange is normal myocardium. And so you can see that it's just kind of this patchy fibrosis that's kind of throughout the muscle. We quantify that as kind of a percent of, the total normal heart muscle. And you can see here in panel C that the red box of the MDX mouse treated with aldosterone has increased fibrosis compared to the mice that were treated with vamorolone and these other two medications. So this was kind of a small animal model that supported the structural idea. We also did some cell work in this paper, and all of it supported that vamorolone has a potent mineralocorticoid receptor antagonism. So why do we feel that's important? Well, I think everyone should realize that cardiac disease is universal in DMD. Every child will get some element of cardiac disease. Some get obviously very severe disease. Some can have mild disease, but everyone will have some amount of it. Similar to skeletal muscle, the cardiac muscle cells lack dystrophin. They can tear. This leads to cell death. This leads to an inflammatory response, and then you get this fibrosis. You saw that on the slide from Dr. Luckmuller of the skeletal muscle. Same thing can happen in the heart. And over time, people have realized that as the level of fibrosis in the heart increases, your cardiac function will at some point begin to decrease and you will start to have heart failure. As we have gotten much better at treating skeletal muscle disease, respiratory muscle disease, these new therapies that are coming, cardiac disease now is really becoming the leading cause of death in muscular dystrophy. The guys are living longer, they're becoming older, and that's allowing this kind of cardiac phenotype or this cardiac disease to show up. And so we really need to look at therapies that kind of modify this oncoming disease that they're experiencing. So just to go through kind of a big picture of cardiac fibrosis, this is a picture where in the middle here, we're seeing direct myocardial injury. I mean, this is basically what is happening because of the lack of dystrophin. The heart is doing its normal job, but in that normal job, the lack of that protein is causing these membrane tears, and you're having muscle cells that are dying. This is leading to different kind of pathways, inflammation, and aldosterone. Aldosterone was that medication that we gave MDX mice in our previous study. And so these types of reactions to the myocardial injury lead to the mineralocorticoid receptor activation right here in the red circle. You see it both in a little inbox here, and it's both showing how it kind of leads to increased fibrosis. So the nice thing, or what we are hoping, is that vamorolone blocks that pathway, and so we get less fibrosis down the road from this cardiac injury. This is just kind of a quick, diagram of how we think of cardiac disease in DMD, starting with basically a normal heart over here in stage A. These arrows are pointing to the lateral wall of the left ventricle. The left ventricle is the big pumping chamber of the heart that sends blood out to the body. So here, everything looks normal. As you get into stage B, you can see that the muscle has some yellow kind of fibrosis in it. And it's just kind of within, but the muscle is still normal sized, and usually the function is normal, but you have this mild fibrosis. This then over time will progress to a dilated cardiomyopathy. The wall will get very thin, and it will basically be just fibrosis. All of your normal myocardium will be gone, and your heart function will be low, and you can develop symptoms of heart failure. So what our goal is to slow down this progression. And you can see, might be small, but there are little ages here under stage A, B, and C. And we want those ages to get much older. Under B, it says ages 8 to 14. We want to get that out into the 20s or the 30s with just mild disease. The techniques of MRI, cardiac MRI, have actually allowed us to visualize fibrosis within the heart. We use a technique called late gadolinium enhancement. Gadolinium is a compound that we give that lights up white on MRI. And so if you think of pictures you've seen in the news or online of a coronary angiogram, when there's like a blockage in the coronary artery, everything lights up and you can see all the blood vessels in the heart. So that's what happens here. But of interest to us is actually what happens when the gadolinium leaves the heart and all the normal blood now is flowing around. And what we see is these white areas that are inside of the normal myocardium, which is black here. And so this is the left ventricle, just like that cartoon we just saw. It's kind of drawn out the same way. But here you see this white line, but next to that arrow, that is actually some of this gadolinium contrast that has stayed in the heart muscle because that scarring is not a normal area and it doesn't have normal blood flow and the contrast doesn't flow away normally. And so you see this residual brightness in the myocardium, in the myocardial muscle. And so this gives us the ability to kind of measure the amount of fibrosis that's in the heart. And so this is the techniques that we will use in the grant. So our main interest is vamorolone, knowing that it has this mineralocorticoid receptor antagonism. Will it delay the onset of cardiac fibrosis and improve cardiac function over time? And so our first objective is to recruit the participants that we're going to study. We are going to focus on the initial clinical trials that were completed studying vamorolone. These kids obviously started when they were 4 to 7 years of age, and they have continued on that medication since those trials. Many of them now are 12 or older, and they have been treated with vamorolone for about 7 years. So we're going to target those participants. We're going to bring them in to perform a cardiac MRI assessment using that technique we just saw a picture of called late gadolinium enhancement. And that will give us a both qualitative and quantitative assessment of how much fibrosis is present in the heart. We will then use MRIs that we've collected from studying other kids with DMD who are not on vamorolone. We'll compare them as kind of historical controls. Those kids are treated with steroids. And so we'll have our control group of non-vamorolone treated and compare it to this cohort of children that have been on vamorolone due to the clinical trials. I also mentioned one of the side effects was delayed puberty. These kids they were too young when they started in the clinical trials, but now they're getting old enough in the early teenage years that we may be able to start to see some hormone levels in these kids that may be closer to normal than kids who are on steroids and may suffer from delayed puberty. So as kind of an exploratory marker, kind of a pilot study, we are going to collect blood on their visit. We're going to look for biomarkers related to cardiac disease, but then we're also going to look at hormone levels related to puberty onset, because that has not really been looked at in this cohort. And so because we have them now getting older in that age range, it's a good opportunity to be able to collect that information. The study eligibility, as I mentioned, this is not going to be like an open study that really anyone can participate in. We are going to focus on the participants in these previous clinical trials listed here in the chart. They have been on vamorolone for a number of years now, over 7 years. We know their contact information. They have been followed by Revirgin. Excuse me. And only if, we have 169 here in our total recruitment pool, we're going to study about 40 of these kids. Only if we're kind of unable to get enough kids out of that would we kind of open it up to say people who have been on vamorolone for a few years, we'll include you in the study. But we want to try and have someone that has been on vamorolone for as long a time as possible to show those potential benefits from it. We have 2 locations, my hospital, Children's National Hospital in DC, and then also with Dr. Khan Hoare. He's the director of cardiac MRI there, a neuromuscular cardiologist at Nationwide Children's. We've worked together on a number of projects, and so that'll give some flexibility for recruitment of subjects. So why does this research matter now? As I said, very important, cardiac disease is universal in DMD. I also mentioned cardiac disease is the leading cause of death in DMD. So there's a lot of focus on skeletal muscle. It is the initial presenting symptoms in children. Loss of ambulation is a major life change for these kids. But we do also have to remember that the heart is going to be affected and we need to address it. And so if we can demonstrate a novel cardiac benefit of vamorolone, this certainly advances our understanding of therapeutics, and it will provide some more understanding of the process and timeline of cardiac fibrosis in the heart. And many patients and families, maybe some of you on this call, are going to be faced with the decision of whether to start vamorolone, switch off prednisone onto vamorolone, and certainly a better understanding of the potential benefit that vamorolone may have on the heart could help better inform patients and families to make that decision. And then how are we going to use the support? Well, this is a observational trial in a sense. With the vamorolone intervention has happened because of the other VBP 15 clinical trials. So we're going to bring them in for a single visit and complete their MRI and their study markers. So the money will help kind of provide support, coordinators, developing the protocol, getting it all approved, and then providing travel support and research costs for the MRI and the blood tests. So in summary, there's a lot of evidence now that vamorolone is clearly differentiated from prednisone and deflazacort, and it has this property of a mineralocorticoid receptor antagonist. We know there's a benefit of that type of drug on DMD cardiomyopathy. It can reduce cardiac fibrosis. And so if we can show that vamorolone helps slow this disease and this progression, hopefully it will prolong life and improve quality of life for these kids. So in the end, just special thanks to all the families involved, the advocates, the donors, everyone supporting Defeat Duchenne Canada, and then all the hard work of our neuromuscular team here at Children's National, just a picture of everyone that comes together to help these great kids. With that, I'll end. Thanks so much.
Thank you, Dr. Spurney. We have a question for you. I've taken deflazacort for 30 years. I started taking it at age 16 after puberty, and I have been diagnosed with tachycardia and take tanolol. I am looking to change to vamorolone, and I understand my heart could potentially improve.
Well, one, I would think that there should probably be some other cardiac medications that already might have been started. Hopefully one of those would be a lisinopril or an aldactone or an eplerenone. And certainly if those are not being used, vamorolone would provide a similar type of a benefit there. But probably at this point, the more direct cardiac medication is probably the primary drug that would be used. What we're hoping to show is that most cardiac medications aren't used now until 10 years of age or so. And if we can show this benefit on the heart and people begin to make the decision to use vamorolone as either an initial therapy or switching over at a younger age to vamorolone, we would have the confidence in saying, well, you know what, we've demonstrated that this is also having some benefit on the heart.
Great. Thank you so much. Let me just take a peek to see if there's any others. I don't see any other questions. But if there are any, we encourage folks online to submit any questions for these 3 grant recipients while we begin to conclude this evening's presentation. So I'd like to congratulate all of you, all of our 2026 research grant recipients. Your work and dedication of your research teams brings hope to families across Canada and across the world. On behalf of the entire Duchenne community, thank you for your commitment to advancing care, understanding, and possibility. Nicola, back to you.
Thank you so much, Lisa, and congratulations again to this year's grant recipients. These 3 new projects, in addition to the research grants we continue to fund this year, brings our total investment in 2026 to $1.2 million. Since the start of Jesse's journey in 1996, we have funded 87 projects from all over the world. And tonight, I am thrilled to announce a major milestone for the organization. In our 30th year as an organization, we have hit our investment milestone of over $20 million in research for Duchenne. This is an incredible milestone, and what a legacy, John. I'm sure Jesse would be very proud. And so this concludes our evening of research. So thank you everyone for joining us tonight. And thank you for being part of this evening, and thank you for being part of our journey. Tonight, we've seen the dedication, the innovation, and the hope that drives every project, every researcher, and every family involved in Defeat Duchenne Canada. We hope you leave with a deeper understanding of the science we fund, the people behind it, and the future we are building together. A recording will be shared soon, and we invite you to stay connected through our e-newsletter and social channels to follow the progress of these projects and the impact of your support. So on behalf of everyone here at Defeat Duchenne Canada, thank you for your generosity, your belief, and your commitment. Good night, and let's keep moving forward. Thank you.